The next talk will be given by Jim Evans along with Kaitlyn Crouch from Utah State. Jim and Kaitlyn are structural geologists. They study rock deformation at a range of scales. Jim's group studies the interaction of hydrothermal processes and rock deformation, focusing on fault processes in the upper 5 kilometers of the Earth's crust. He is a former editor of 2 journals, the Journal of Structural Geology and Lithosphere, and would happily volunteer services as an editor for something, especially if it helps younger workers. Jim, take it away.
Thank you very much. And do we just see the slides? Is that okay?
Yeah, it looks good.
Okay, terrific. I'd like to thank everybody for inviting us to give this talk and thank everybody for presenting such interesting talks to date. Before I get started, I want to really reach out and thank especially Sam Webb and Sharon Bone at SSRL. We were able to do a significant number of analyses in the past year remotely, and this is going to enable Kaitlyn to finish her master's degree relatively on time and be able to go on to her PhD. So I just want to thank the folks at SSRL. I'm going to motivate this talk by bringing something a little bit different to this session, and that is I study earthquakes. I study earthquakes as recorded in the rock record, and I study earthquakes in the rock record from a more geochemical and structural geology perspective. I am not a seismologist, but yet the seismologists, I think, have handed us in the geochemical and structural geology community a number of gifts. My feeling is that, at least in my academic upbringing, when geophysicists tell you that something you're working on is important, you better grab that ring and run with it for as long as you can. In the recent National Academy of Sciences report that was discussed earlier today, it was revealed or discussed that unknown to a lot of people, the notion of an earthquake has really expanded in the past 10 or 15 years, and it has left rock mechanicists and geophysicists with a real open field in terms of understanding the concept of fast slip versus slow slip. Aseismic slip have become really, really important notions. How fast does an earthquake move? Used to be thought to be a relatively simple and easy question to answer. We now have come to realize that there are a whole range of slip behaviors, and these have been recorded in the rock record to a varying degree, although many of us are still struggling with how do we understand these records in the rock record. So we might think of a fault zone as shown by this work from a recent structural geology white paper that was sent to the NSF. And we want to focus in today on the very upper part of the Earth's crust, where there's another geophysical debate taking place, which is how is slip distributed in the upper part of a fault zone. There are a number of models that use inferred from a variety of indirect measurements to understand or to think that the amount of slip that's actually recorded at the Earth's surface is less than the maximum slip that may be at 2, 3 to 10 kilometers depth. So where does the slip go? How is the slip accommodated? How fast is all of this slip? These are now really open questions to the earthquake seismology and structural geology communities. We tend to think of these problems in terms of what might be thought of as a sort of canonical fault zone model in which many faults are represented by a fault core. Typically, we think that the fault may represent or have a relatively narrow, and in some cases extremely narrow, slip surface that is embedded in a damage zone. That damage zone may be on the order of 100 to 200 meters wide. The slip zone itself may be as narrow as a few millimeters. These damage zones are often expressed as zones of significant fluid rock interactions, veins, chlorite, zeolite, clay alterations that alter, say, the quartzo-feldspathic protolith. And geophysicists and rock mechanicists have come to recognize the importance of this off-fault deformation as perhaps being important to understanding how earthquake energy is distributed in and around a fault zone. I'm not going to go into the details here, but as I said before, when the geophysicists tell us that these are important processes to understand, I like to sort of address these. And I want to come at these from a geochemical perspective. That damage zone and in fact the fault slip zones are regions where there are significant amounts of geochemical signatures, a significant amount of mineralogical alteration that takes place and are recorded in these rocks. And I think we can use these to go back and say, what was the experiment that the earthquake ran? What were the conditions at which that experiment occurred? So these are strongly influenced, moderated, or controlled by geochemical alteration or hydrothermal processes. The big questions are how and when is slip distributed along and across faults, and how is that coseismic energy distributed in and away from these fault zones? Our specific questions that we address using a variety of X-ray techniques is how do we, or can we estimate what peak fault zone temperatures have been along these faults? That helps us constrain the amount of energy, the energy distribution within the fault zones. And we want to get at the micro mechanisms, the deformation mechanisms, and the interaction between the deformation mechanisms and the geochemical processes that we think are interrelated with these deformation processes. So we do this by studying a series of faults. We have studied small faults, which I'll talk about in a little bit, and we have studied large faults, including the San Andreas Fault, which is an active strike slip fault in Southern California. And we have also, Kaitlyn has worked on the San Gabriel Fault, which is an extinct ancient fault that is an analog to the deeper portion of the San Andreas Fault. So recently, Carly Studnicki has just finished her degree working on the San Andreas Fault, in which we had the opportunity to study fresh core from across an almost entire section of the San Andreas Fault. And with these core, these are very well preserved fault-related structures that we can then extract from the fault zone itself in a relatively unaltered setting. These core come from between 200 and 400 meters deep within the rock, and these are just below the quaternary deposits. As most geologists in this audience know, our typical analyses might be and we have done, analyses that include whole rock geochemistry using X-ray fluorescence and ICP-MS whole rock geochemistry, X-ray diffraction analyses to understand the nature of the mineralogy in these rocks. And as we all know, these tend to come from point-wise samples indicated here schematically by the little red squares. So we can get very high precision, but even at that precision, we see that we're collecting data, if you will, from a relatively large volume. And it doesn't tell us as much about what's taking place at the grain scale as we might like. We also see that we have no indication about the redox conditions, which I will show later might be very important in some of these cases. So our first set of analyses that we present today show us what we use in terms of the San Andreas Fault. This is an example of the macroscale XRF analyses that's done in line 6.2 at SSRL. And this helps us further understand and start to examine the distribution of relatively common transition elements within the fault zone. And one of the things that we see repeatedly at all of the scales of analysis that we have done is this extremely strong correlation between the presence of higher concentrations of transition elements, iron, manganese, titanium, nickel, chromium, as you'll see later, in and around these narrow slip surfaces along which most of the fault slip has occurred. So on this case here, you're looking at the analysis of the, looking at an XRF map here, focusing in on just iron, but iron here is a proxy for the other transition elements. And you can see away from the slip zone is shown here in the middle part of the fault zone. You can see these webs of fractures, these web-like fractures that are decorated and marked by concentrations of iron and other transition elements. You can also see the blue and blue-green regions. These are places where there's relatively large amounts of potassium and sodium calcium feldspars. Right in and around the fault zone, we see this concentration of relatively large amounts, up to probably about 4 or 5 weight % total iron within the slip zone itself. As we focus in now and go to, say, beamline 2-3, we can start to tease out what this sort of structure is. And here's an example of that damage zone now within the fault zone, but away from the principal slip surface. And again, we can see the concentration of these transition elements. In this case, we show the titanium, iron, and I can't see the last one, sorry, chromium. We can see are starting to become distributed and concentrated along these slip zones within this quartzo-feldspathic host rock. There is a range of geochemical analyses to suggest that the temperatures of these alteration assemblages might be on the order of at least 150 degrees, perhaps even 200 degrees C. And remember that these rocks were collected from about 200 meters depth. So that would be a hydrothermal alteration process that's recorded in these rocks. As deformation seems to proceed, we develop what we call cataclasites, or highly sheared rocks. Again, notice the association of these transition elements concentrated in and around these cataclasite zones. And you can kind of get a sense that there's sort of a feeder-like system of these networks of fractures that are providing conduits, if you were, of fluids to help supply or remobilize some of these transition elements in and around these damaged rocks. A second analysis or a second expression of the rocks that we're interested in are these extremely narrow slip surfaces that we have focused on in some of these San Andreas fault rocks. Here we can see a very precise analysis, again, focusing on the transition elements, these very narrow slip surfaces, but we'll note that in detail in optical, scanning electron, and electron EBSD analyses, we see that there's evidence for a relatively rapid slip in the form of certain types of fractures that are off the slip zone itself. In this case, we can see these little fracture zones splay off, and they are again decorated by these transition elements. And there's also these sort of wavy amorphous materials within the fault zone. Recently, Hauser et al. From Alexis Zalt's group here at Utah State University has done transmission electron microscopy. And we've done a number of other analyses to suggest that these are iron titanium rich, possibly melt quenches that occurred along the slip surface. These would be called pseudotacholites or what are sometimes referred to as a silica-rich gel, which are indicative of an earthquake slip, very rapid slip along these fault surfaces. And so that's what we think perhaps these very amorphous surfaces or decorations along the slip surfaces here. The second site that we've examined is the work that Kaitlyn Crouch has been doing. This is again from an exhumed ancient example of the San Andreas Fault. It's called the San Gabriel Fault, which was active between 5 and 13 million years ago. It had about 40 kilometers of right lateral slip, and it has since been exhumed to near the surface. And again, Kaitlyn was able to access the fault through both a core that went through the fault zone and also some surface samples that colleagues of ours collected some years ago. Kaitlyn has done the traditional analysis in terms of looking at the mesoscopic structure. Here you can see the undeformed gneissic structure, the deformed cataclasites in the damage zone, and then the highly sheared materials. Having gone through this analysis with X-ray diffraction, whole rock geochemistry, and also optical microscopy. And here she is doing her work last year before the pandemic hit, learning how to do synchrotron work on line 2-3. That work that she has focused on has examined, again, the concentration of these transition elements. Here, there's possibly the evidence for some hydrothermal alteration, but also the presence of something that we might think are what we would call pressure solution or stress solution seams. And that is, instead of just pure shear slip along these surfaces, there may also be a solution process that's taking place within these faults. Here's a tricolor map looking at iron, calcium, and potassium within her samples. These are three elements that tend not to associate in what we now would call the ultracataclasite. This is the 2 to 3 centimeter thick fault core that some other workers in the past have suggested received or accommodated much of the slip along the San Gabriel Fault. Again, intense amounts concentration of iron, and you can see that there was deformation and deposition of calcite or calcium-rich veins associated with that iron-rich slip surface. The second type of analysis, and this is actually where I started my synchrotron work, and so I am very much still a neophyte to the whole game. But this is where I started the our work, was to test something about what the slip surfaces were on a series of faults that we found here in Utah. And this is the Wasatch Fault in central Utah. This is an active fault. It produces magnitude 7 to 7.5 earthquakes. And it is the significant source of seismic hazards to the central part of Utah. On the right-hand side is a photo of one of these slip surfaces. You'll notice the beautiful wavy pattern to that. You'll also notice that there are iridescent patterns to the fault surface, and those iridescent patterns were something that I had hypothesized some years ago, where the evidence of very localized disparities that banged into one another during fault slip, and that these zones of iridescence were places where iron was probably being transformed and being reduced. So we first tried to analyze that using a variety of samples, and this is where using the X-ray fluorescence and XANES analyses on the beamlines became very important. One of the advantages we have is that in some of our samples, we do not have to prepare much of a flattened surface because nature has done this for us. This is a natural slip surface from one of these small faults, and we found fairly early on that the slip surface itself was on the order of several microns to maybe a millimeter thick. We did some early X-ray photoelectric spectroscopy on these analyses to indicate that there was in fact some iron reduction and that the highly polished slip surface was on the order of just a few grains thick. And so what was happening is that at the microscale level, we saw transformation of hematite to what we would call micromagnetite along these fault surfaces. When we took this into the XRF mapping world at 2-3, we were able to map the presence of the chromium, magnesium, and other transition metals. Here you can see the iron, and we're doing iron mapping. We can do iron 2 mapping and iron 3 mapping. And we also look at cross sections, and again, we see these amorphous stringers along the slip surface in which iron is very well expressed at and near the fault surface, again on the order of just a few microns for the most case. There's also concentrations of vanadium and concentrations of titanium along these slip surfaces. We have begun to do the XANES analyses of these, as was discussed in the previous slide, although not with as much robustness yet, but we are still working on and looking at the nature of iron reduction along these fault surfaces. But we do think we do see evidence for these for iron reduction. So that gives us hope that we can use XANES to help understand what the nature of the temperatures might have been along these fault surfaces. Now, when we do that, we do see that there are examples of, there have been experimental analogs for this. For example, there are sintering experiments in the material science world in which small amounts of magnetite can be created at relatively high temperatures. And when we take a look at what we've done to date, we have now also learned from the work, again, from some folks in our group, from McDermott et al., and also from the recent work by Hauser et al., that these transitions I earlier on hypothesized occurred at, say, 300 or 400 degrees C, more likely for the Wasatch Fault samples occurred at somewhere between 800 and 1,000 degrees C. So we think that these iridescent spots are an example of micromagnetite development due to very, very rapid fault slip on these narrow fault surfaces. This has got importance in terms of understanding and constraining the nature of fault energetics, which then plays into the questions that I posed at the beginning. We hope to continue this work with future work on manganese. I'm also going to return back to some of the work we did on vanadium. There's a new paper that came out just yesterday about vanadium, and then also to look at nickel and chromium, and also look at some other elements based on the work that has been presented here and things that I've learned in the last few hours. So some conclusions, something I wanted to echo that everybody else has said, the multimodal analyses are really, really important. Using X-ray fluorescence and XANES at the synchrotron have been really key, and merging them with electron microscopy, optical microscopy, whole rock geochemistry, and other analyses, TEM in the case of Leah Hauser. So we think that the XANES analyses suggest that there's an iron 2, iron 3 reduction associated with the peak slip. And we also think that the transition metal distributions in the damage zones and along the slip surfaces indicate some sort of hydrothermal, very intense relationship between hydrothermal alteration and deformation. And in some cases, we think that these processes occurred at less than 1 kilometer depth. I want to make it very clear that this process is hydrothermal, calling upon hydrothermal processes at relatively shallow conditions in these faults, and evidence for seismic slip at these shallow, actual seismic pseudotechlite formation is somewhat outside the paradigm of traditional fault zone analyses. And so I think we're starting to sort of push some boundaries here in terms of understanding how faults work. Thank you very much for your time, and I appreciate everybody's work in putting this together.
All right, thank you very much. Very, very interesting talk. We have time for a question or two. Are you also, do you have plans to look at sort of more textural information in terms of this, the anisotropic structures that develop in these features as well?
Yes, we do. We've been talking off and on with Sam. I'm sorry, my timer went off. So I've been talking with Sam Webb about that, and yes, we have been thinking about that, and that's actually sort of a cool point about having attended this workshop, is I'm learning about those techniques and who might best to be able to do them and that sort of thing. So absolutely, we want to work on some of those textual questions.
Yeah, that seems like a good way to go. But in addition, how do you relate this to sort of larger scale fault zone processes? How do you,
well, this is the larger zone fault zone process. So these slip surfaces, we assert, are where the action happens. That's where the coseismic slip of 3, 4, 5 meters occurs. The damage zone around them is 100 meters or so. And most of this material is taking place, deformation is taking place at the grain scale, right? And then we integrate it over that wider zone. And so we relate that volume, if we will, the volume and compliance is a term that the seismologists use, or reduction in elastic moduli. We can estimate those now based on our compositional studies. So we can then sort of inform rock mechanics and seismology models about what the actual material properties are of these zones, starting from the grain scale, but then working up to these larger scales.
Okay, we have a question from Peter Heaney. Jim, what is responsible for the iridescent effect?
So again, what I think that is if you look in the materials literature, that's actually a piece of evidence that material scientists see. But imagine, so a model for earthquakes has been what's called the asperity model, that a fault zone has rough and that there are bumps at a variety of different scales. And that those bumps, once they start to move, if you get a critical distance of slip, those bumps smash into one another or slide past one another. And those are places where there's very small in space and very short in time smacks, if you will, or bumps of those asperities bam in, hit each other as fault slip occurs. So I think that those are evidence of asperities hitting along the surface during a seismic event, and that the heat is very localized in those zones, and that's what's causing this hematite to magnetite transition.
Okay, there's also a question from Ryan Tapero. Do you find it necessary to make self-absorption corrections for FEK edge, especially for thick iron in slip faults?
Yes, we are going to have to do that. And that's, again, like I said, I'm still a novice. And so that is totally something that I'm sure Sam's going to teach me how to do. And even though I can't see Sam, I'm sure he's smiling.
Okay, he's on the spot now. He's got to do it. Okay, thank you very much.